Okay, so we're about to start. Thank you all for coming. I would like to introduce our colloquium speaker today, Professor Sara Seager. It's been a pleasure to have her here visiting us and our telescopes and now giving what I think is going to be a very interesting colloquium. Let me just give a very brief introduction to her, because if I do a proper introduction, then it's going to be a 2-hour seminar, because it will be really long. But just let me say that Sara is an astrophysicist at the Massachusetts Institute for Technology. And she's not an observational astronomer, as we have more or less discovered, but she's more a theoretician and also a data analysis. And she has been worked on the field of exoplanets for the past maybe 15 years. And I think it would be fair to say that the field of extrasolar planets and the discoveries that we see nowadays and that she's going to introduce will not be the same if Sara hasn't worked on this same field. Another thing is that before she joined MIT, briefly, Professor Seager was 4-year a senior researcher at the Carnegie Institute, and he did her PhD at Harvard University. And now I'm going to say that she's also a co-I of the MIT MIT-led TESS, the terrestrial exoplanet mission for characterizing and finding and later characterizing extrasolar planets on the whole of the sky. She is also chair of the NASA Science and Technology Definition Team of a Prof class starshade. I guess this is what her talk will be about. And I think this is going to be really nice, because this is a talk about the future, about not what we're doing now, not about what papers will be 2 years or 5 years from now, but 20 years from now. And it will open our eyes to what is possible and what is not possible for our generation in the near future. She's also the recipient of several awards and prizes, which I'm not going to relate here. So I just introduced Sara. Thank you for being here.
Hello. Thank you for coming to my talk today. I'm very pleased to tell you about exoplanets. And I'm starting out with this beautiful image of a dark sky. Of course, all of you know you won't see this with your eyes, but rather from a photograph. But what some of you may not know is that now astronomers believe, statistically speaking, that every star in our Milky Way galaxy should have at least one planet. So the next time you're out on La Palma, hopefully you'll have better weather than we had when I was there, but you can look at the stars and you can wonder what kind of planetary system is around that star. And what I'm going to talk about today is I'm going to hit 2 or 3 of these main points, but I'm here to try to convince you. We call it the search for Earth 2.0. That, we know, well, obviously we know where the nearby stars are. We know that small planets are extremely common. We know what kind of planet we're looking for. We know how to identify a planet like Earth. And right now we are developing the required space telescopes. So that's sort of where we're at in the field. We feel like we're just like on the verge of being able to find the Earth. However, as many of you know, sometimes a project can take many years or decades to actually come to realization. So it's a long process. But before I get started, just for those who are working on exoplanets and those who are not, I'm going to take you on a tour of a few of the really most interesting planetary systems. And I'd like you to make a note of this, eyes on exoplanets, because later on you can all Google this and download it for yourself or your students or your family, and you can use the software too. I'm not involved with this software, I'm just a big fan of it. And I hope that you can all use it later. So here's the software. And what it does is it can actually show you from your vantage point on Earth. They didn't have us here, unfortunately, but don't worry, they don't have Boston either. And actually, it'll show you from wherever you want. Let's see. Okay, well, let's pretend we're in Asia right now. And it'll show you the stars from your location. And these stars that are highlighted are the ones with exoplanets. Right now, there's about, let's say, 2,500 stars with confirmed planets, another 2,500 or so with planets. We're not 100% sure they're there, but we're like we're sure on the whole for most of them. So actually, in this software, you can scale out to, hold on a second. You can scale out and you can see where all the stars with planets are. It's operating a little slowly here, but you can see there's the moon. And eventually this will take us out to our galaxy to show you the picture of what it looks like. So what I'm going to do, okay, here it's showing you our solar system, and it showed you, just flashed by where Kepler was and where the epoxy spacecraft is, Pioneer, Voyager. It's taking you really far out. And eventually it's operating kind of slowly, but it would take you out to the Milky Way galaxy to show you where the stars are with planets that we know about. So bear with me here. See, there's thousands and thousands of stars with planets right now. They're all actually clustered because unlike some of you who may work on extragalactic things, we really can still only see our nearest neighbors. So we are talking about our own galaxy, the Milky Way. So here's what we think our Milky Way looks like. Here's our sun, and here's where all the planets are, quite nearby. And these, we have a stream headed towards the galactic bulge because of microlensing surveys. What I'm going to do now is search for I just chose 2 or 3 planets that are my favorites. Anyone who works on exoplanets, wait, how many people here actually work on exoplanets? Okay, so the people who work on it, they're all going to know what these stars are when I type in the number, because they're all well known for one reason or the other. It may seem like we know every star by name, but that's not so. So this one, HD 189733, it's one of the nearest stars with planets. This says that it's 63 light years away. It's got this planet orbiting it, just one. It's called a hot Jupiter. But what I wanted to show you was a comparison with our solar system. And look, on the outside, there's Mercury. And there's the planet. So this hot Jupiter is 10 times closer to its star than Mercury is to our sun. It's a very hot planet. It's heated to well over 1,000 degrees Kelvin. And there's many, many more like that. There's a sort of cute thing here that, how long to travel here. This is just, for public outreach. By car, if you want to go by automobile, 60 miles per hour, 700 million years. It just helps to convey, actually, usually to non-astronomers, just how vast the distances are to these other stars. I'm going to show you another one. This one is from the Kepler Space Telescope, Kepler 11. And this one, I like this one of my favorites, because it has a number of different planets. This just takes you to, look at that. 6 planets shown. And they're just named kind of in order of their discovery. But do you like how it looks? Kind of looks like our solar system, huh? But if you actually compare with our solar system, you'll see something odd. And look what it's showing you. Look where Mercury is. So 5 of those planets are interior to what would be Mercury's orbit. And all 6 of them are interior to what would be Venus's orbit. We call this a compact multiple planet system. And they're all transiting, so they're very flat. Now, when I first learned about this system, I assumed that all the planets were very small, like Mercury, like rocky small planets. But you know what? They're not, actually. We couldn't really find them if they were that small. But some of them must have a hydrogen and helium envelope, a small one. But they're of such low density, they cannot be a small, tiny, rocky planet. They have to be a bigger, slightly bigger planet that's low density. So in exoplanets, we say that anything is possible within the laws of physics and chemistry. And it really just means, at least for planet formation, that it's a random process. And there's many things going on. And I'd like you to know that there are many, many systems like this, many compact multiple object systems. Perhaps several have been found, but many more have been found with just 3 planets or so. And just one of the more interesting facts of this is, people think they formed further out and migrated inwards. And for a number of these systems, there's resonance. Like how our moon is in a 1-to-1 resonance on planets. But instead of being in a perfect resonance, like instead of being in a 2-to-1 resonance, they're just slightly off. So, for example, one planet might orbit in 10 days, and the next one out, instead of orbiting in 20 days, it orbits in like 19.5 days. So a huge number of these systems, they're almost in resonance, but not quite. So the planetary systems have given the dynamicists and planet formation people a lot to think of. Let's see, I'll just show you 2 more, because this is just the introduction of my talk, but HD 80606. Unlike the other ones, this one is kind of a one-off. We only have 1 in this category. This one's a very unusual planet. Look at its orbit. It's like a comet. It's a planet. It has this extremely unusual orbit. And what's even more interesting is it actually transits its star. It transits, and I'll show you what it looks like. It's got about a 100-day period orbit. So there's Mercury. And I want to tell you one interesting thing about this planet. There's a lot of interesting things about it, but this actually will let us show how, see, you know how the Kepler's law, the planet is going around quite quickly? Let me get rid of this. So that planet, HG 80606, it's an elliptical orbit, so remember it moves slowly. When it comes by the star, it zooms by. Well, people have measured with the Spitzer Space Telescope how that planet heats up. It's getting flash heated when it orbits very close to the star, and then it cools down. And from the rate at which it cools, we hope to learn something about the atmosphere. We call it the radiative timescale. So there's a whole bunch of planets out there. I think I'll just show you one more. So remember, most of the planets I've shown you are close to the star. They have a selection effect for that. This particular one I'm showing you is a little different. HR 8799. This one has planets found by direct imaging. Again, it kind of looks like our solar system if you just take a quick look at it. But if you compare with our own solar system, look, there's Jupiter, and these planets are much further from their star than Jupiter is to our sun. So these ones are big, giant planets. They're young, they're hot. They're found by direct imaging, and they're quite far from their star, essentially as far as Pluto or further. So what I had hoped to convey to you from this program, which I hope you'll explore yourself, is that planets fall in a huge variety of orbits. It's a lot is going on in exoplanets, and I'm going to summarize this just with a few plots now, because this is what you normally see in a talk. Instead of seeing the individual systems and looking at how they look, you just see them all kind of collapse on here. And this plot is showing you planet mass in Earth masses, and it's showing you the semi-major axis. It's scaled in a kind of an awkward way, but you can ignore the scaling for now. I just want you to see that the planets here, they're all found by different techniques, all the different symbols, but this is a logarithmic scale. So the planets, in terms of their mass and semi-major axis, are spanning many orders of magnitude. So many. And you can see here where Earth and Venus are. These are the solar system planets. So this is planet mass, or mineral mass, and this is semi-major axis. It's normalized by the snow line. So here are Venus and Earth, Uranus and Neptune, Saturn and Jupiter's hidden on here. But you can see there's so many planets, right? Planets are everywhere, and there's a selection effect where we don't see planets. It's because techniques can't reach there yet. Now, these are the directly imaged ones, like the one I just showed you, and look how far away they are, 100,000 AU even from their star. Unbelievable to have what we think are planetary mass objects so far away. So it's pretty remarkable, actually. Now, these are just, the colors are just showing you all the different techniques. Although I'm not going to describe them today, I just want you to know that each technique has its kind of heyday. There's usually a decade where one technique wins out. It's just now we're in the zone of transiting exoplanets. I think that the direct imaging folks are next, actually. Microlensing takes this middle chunk of the diagram. But kind of in the interest of just conveying to you just how many planets we have now, this is showing you now planet size and orbital period. So instead of planet mass, it's showing you planet size. Planet size, 1 Earth radii, 10 Earth radii. So there's about 1 Jupiter radius here. And this is orbital period in days. So 1-day period orbits. It's amazing, right? Some planets have only 1-day period orbits. 10-day period, 100-day period. This is actually the Kepler data. And the different symbols are just showing you how many planets are in each of those. But I just wanted you to see that there's just so many planets, thousands and thousands of planets. But at the same time, this zone down here, this would be where Earth would be at about a 300-day period and 1 Earth. It's all blank there because we're still having trouble finding planets. But out of the summary part of my talk, there's one point I'd like you to walk away with. And if you only remember one thing from the talk, I hope it is this plot. And this plot has now been updated, but it hasn't been updated in a robust way. But on the whole, this is showing you it's corrected for biases. The planet size compared to the fraction of stars with planets. Now, this plot is for short periods less than 50 days, but now we believe this holds out to quite long periods, 200 days from Kepler data and even longer from microlensing and other data. But what this is showing you, it's showing you a cartoon of Jupiter. It's 11 Earth radii. Neptune is 4 Earth radii, and there's Earth. And look at this plot here. So in exoplanets, we often have plots that are not believable, but this one, what you're supposed to see is how much more common small planets are compared to large planets. We had, I think, a mistaken belief that there is always an end to planet formation. That would be a Jupiter mass or Jupiter-sized planet, where a planet starts to form and accretes rock and other material, and eventually literally just had a runaway growth process where it just sucked in all the material from its feeding zone, and the planet would grow and grow and grow until there's no more material left. That's sort of the simplistic overview. So I don't know about you, but I always thought that a Jupiter-mass planet would be the most common. What this is telling us is that the smaller planets of perhaps Earth size, or certainly of 2 to 3 Earth times the Earth size, are literally the most common planet in our galaxy. Now, why is this so important? It's because in our own solar system, we can arguably say that we're not even sure how our own Neptune and Uranus formed. They somehow got truncated in that runaway process. People had a story where they didn't have time because they're in the outer parts of our solar system, didn't have time to gather all that material before the disk dissipated. But here I'd say it's one of the, I was going to say if I was here for a few months and just had some time to think, or if I was a student, I would consider attacking that problem. How do we form these planets of 2 to 3 times the size of Earth? They're not rocky planets because most of them have a measured density. A lot of them have a measured density showing they must have a hydrogen-helium envelope. They have low enough density. They have to have some kind of envelope. So that's what I'd like you to walk away with. Small planets are common. And so to summarize this introduction, I'm adding a bit more information here because I didn't have time to go through all the details, but small planets are actually quite common. We don't know how common they are. I put some numbers here sort of without error bars, but these are from the latest papers that people make a very careful study. So they'll take the data in the Kepler field, 150,000 stars, and they'll actually say how many planets are found, and they'll actually go star by star and say which kind of planet could have been detected around that star, given the faintness of the star, the noise of the star, etc. So lots of work goes into these numbers. But we want to say that stars, Earth-sized planets, are very common, and people really want to know in the habitable zones in particular. They say, let's say 5% to 20%. It may not seem like a huge number, but there's billions of stars. So we think that these small planets are really, really everywhere. So in this talk, we know where the nearby stars are, and I showed you the eyes on exoplanets to show you where some planetary systems are. We know how common small planets are. I have to put some caveats as I go through my talk, approximately. We know they're common. And now I wanted to tell you that we know, or we think we know, what kind of planet we are looking for. Now here we have the habitable zone concept, where we'd like to find a planet. We have a kind of a bias, some of us in the field. I mean, all planets are equally exciting, usually. But we're really hunting for planets that are the right temperature that they might be able to host life. And we call this the habitable zone. The cartoon is showing you here that planets like Earth that are rocky with thin atmospheres are heated from the outside. And they have a greenhouse effect, of course, but the distance from the star is really one of the main critical inputs for temperature. So we have the Goldilocks zone, not too hot, not too cold, but it would be just right for life. That's a cartoon. And here's here's a schematic. How many of you have seen this picture? So, if you work in astrobiology or planets, or you teach a class on the solar system, this has been an iconic picture for many decades. And what it's showing you is it's called the circumstellar habitable zone. This is showing you the mass of a star compared to the sun. So this is our sun shown in yellow. This would be a bigger star. Here would be a smaller M star, showing you at about half it's just a schematic. And this is showing you the solar system planets, okay? So radius, orbital radius relative to Earth's. Typically, people are assuming a carbon dioxide water atmosphere. And this here just shows you because, small stars, M stars, they're less luminous. They give off less energy. So that habitable zone would be much closer to the star. But I just want you to know where this comes from, that too close to the sun, or too close to the star, the planet would get very hot and the oceans would evaporate. And we think this happened to Venus, that ultraviolet radiation split apart the water vapor and the hydrogen escaped to space. And you just have all the water evaporating, going high in the atmosphere, hydrogen escaping away. And eventually your planet would be so dry it wouldn't be habitable. On the other side, condensation of carbon dioxide. Mars has frozen carbon dioxide. And so if the planet is too far from the star, the greenhouse gas of carbon dioxide and water, they'll freeze out. And now the planet can't be habitable. So I hope for some of you, I hope that at least half of you have heard of this concept, because this is sort of carried forward But just like how now planet formation has had to change because of all those crazy planetary systems, our sort of concept of what's a habitable planet is also changing. That was for Earth-like planets. And so now I want to summarize a revised habitable zone. And I'll say that in any field, you know how people fight? I don't know if that happens in your field, but some people just get very angry. They're kind of attached to the old picture, and they just fight. We've had some unfortunate, I don't know why people have been so unhappy with the revised habitable zone. You know, we can't help it. Nature has been diverse and has provided us with all these different kinds of planets. I only showed you a tiny tip of the iceberg. And we expect that diversity to flow to the atmospheres also. Think of our own Earth for a moment, and we're worried about climate change, right? Global warming. And that's for parts per million of carbon dioxide. We're about at 400 parts per million. But imagine if our Earth had 800 parts per million, or if our atmosphere was much more massive. We don't know why our atmosphere is, about a millionth the mass of Earth. We don't know where that came from originally. We had outgassing. But will a more massive planet have a more massive atmosphere? Probably. So in this picture of the revised habitable zone, it's the same picture as before with mass of star relative to the sun. And now we have the radius of the orbit relative to Earth's. And what I've shown here is I actually had a graphic artist make it from the models. So this blue region is the sort of traditional habitable zone considered an Earth-like planet. And I think you can see it falls kind of close to Earth because the models in this particular team, Jim Casting has been the one moving this concept forward for many decades. They found an inner edge of their habitable zone at 0.99. That was a little uncomfortably close. But it's, there's problems with models because they don't include clouds properly. It's really hard to say exactly where this habitable zone is. That's why it's a bit blurred at the edges. And these are real exoplanets that we know of around different star types. And again, this slopes downwards because for smaller stars, the habitable zone is much closer to the star. Now, the yellow and blue are new here, and that's what I want to explain to you. And this is all captured in a review article that I wrote. So some of this work exists and was done by other people. If you read the article, you can get all the references. But in the inner edge, this is where people are fighting. The question is, how close to the star can a planet be and still be habitable? And the reason we're so interested is, remember, when I showed you the stars with planets, many of the planets, well, I could have been biased, right? But many of them are so close to the star, they're easier for us to find right now. So we'd like to know how close to the star could a habitable planet be. On our own planet, water vapor is our biggest greenhouse gas. And so we wonder, could we have a planet with less water vapor? If we had less oceans, we would have less water vapor in our atmosphere. And depending on the relative humidity, I think it could imagine a planet with less water vapor, less relative humidity. That planet could be closer to the star. It would absorb less radiation, and it just wouldn't be as hot. So it could avoid the runaway greenhouse being closer to the star. I feel like here you know more about relative humidity than most of us, because when you're on the mountain and it's even a clear night, like when I was there, I got to go to La Palma a couple of nights ago, and I woke up in the middle of the night because I really wanted to see the dark sky. And it was so cloudy, like it was so foggy, I couldn't even see like to where you are. But I looked on the webcams online, and they were all showed clear. So just on the mountaintop compared to the observatory residence, it was clear. But the telescopes still weren't open because the relative the humidity was too high. And they don't want, like, condensation and stuff. So that number is something it's hard for us to model. We don't totally understand it. But we're working on models to understand how close that inner edge could be. Wouldn't it be great? It's true that the habitable was close to half an AU. I think we have a lot more chance of finding planets and things like that. Now, the outer edge, you see this, actually, it kind of goes on forever. And right here in this dark blue is a very interesting concept. And this is that some planets that are more massive than Earth may be able to retain hydrogen. We're imagining a big rocky planet that's colder, that has hydrogen in its atmosphere. You know, from our own Earth, we don't have hydrogen. It's a light gas. It will escape to space. The analogy we use for the public, it's not totally right, is, when you have the helium balloon and you let go, it floats away. There's some planets where their gravity would be strong enough, they'll be cold enough to hold on to it. And if you have molecular hydrogen, it is pretty much the most nasty greenhouse gas imaginable. Molecular hydrogen has collision-induced opacities. I don't know if any of you work on white dwarfs and you deal with collision-induced opacities. So molecular hydrogen, it's a homonuclear molecule. So it doesn't have a dipole moment, and it doesn't have the normal absorption bands, like water vapor has specific bands. But if you're at high enough pressure, that homonuclear molecule gets an induced dipole moment from collisions. And then it absorbs continuously from the red through the infrared. So it's a nasty greenhouse gas because it has such a wide absorption. It absorbs pretty much everywhere in the spectrum. And people have made calculations that show that the habitable zone for that kind of planet with hydrogen actually extends further out. And it may actually go as far out as several astronomical units. So you could have a planet that's massive with a hydrogen atmosphere that has a lot of opacity. It absorbs a lot, and it can become habitable. And that was by Gaidos and Pierre Humbert. And even earlier than that, there was an author, David Stevenson, who wrote about rogue planets, planets that may have been kicked out of their planetary system. Perhaps even a special one has the right thick atmosphere to trap heat generated by radioactive decay. So although we're kind of all over the place here, we have a lot of concepts. And that's for the future when we can make observations of such planets. So when I say we know what kind of planet we're looking for, I have to add we think. But we're looking for a planet that's potentially habitable, a predominantly rocky planet with surface temperatures suitable for liquid water. But exactly what that planet is, it could be a huge number of different types of planets. We know how to identify planets. So this is supposed to be, it sounds like we're so sure of ourselves, but we're not really totally. We think we know how to identify a planet like Earth. Now here's a beautiful Apollo image of Earth. I don't need to tell you that we're not going to see that for another planet. That's probably, that would take 50-meter telescopes in space. It's not going to happen now. But on the left, on your right, that is actually a real photograph of Earth. It's a real image of Earth taken by the Voyager 1 spacecraft at 4 billion miles away. And what I love about this image is you see the red band. It is actually scattered light in the camera optics. But I like it because it represents the zodi, the zodiacal dust. To me, when we get an image like this of another world, we actually may well see a band like that from, asteroids are colliding with each other and they generate dust which scatters red. In fact, one of our biggest concerns about the search for another Earth is the zodi. Because if other planetary systems have exozodi in excess of what we have, it's a big noise source for us. And I hate to say that one of my hopes of coming to the Canary Islands was to see the zodi. Have any of you seen the zodi? I'm assuming there's a lot of observers here. If you look at like sunset and you can see a glow, and October is supposed to be the best time to see it, fall and spring when the ecliptic is right. But the exozodi could be a real problem. And actually one of my favorite plots is this one from my host Enrique Palais, showing you what our Earth spectrum actually looks like. This is a real spectrum of Earth in a globally average sense. And this is showing you all of visible wavelengths. This is the blue going through 2 microns here to a few microns. And so this is visible through near infrared. And what he has done here is, you can talk to more about it later, but he's used Earthshine, looking at the dark part of the moon that's slightly lit up from Earth's reflected light. And he has extracted what Earth's spectrum would look like. You'd see blue from Rayleigh scattering. You would hopefully see oxygen and ozone, and you'd see water vapor features. And he also did a brilliant experiment getting a transmission spectrum of Earth. This is a little more complicated, so you'll have to talk to him later or, mull it over in the slow parts of the talk. But he used a lunar eclipse when rays from the sun went through Earth's atmosphere and refracted slightly and hit the moon, and then bounced back to Earth. And he's able to extract this. This is great work. And it's showing you essentially what our Earth looks like from far away. When we talk to the public, we call you can use this too. It's a funny phrase I just heard called squiggly line science. We hope that we're going to get a spectrum like this. This would be for a planet far away. This would actually be great if we could see real features and try to identify what they are. So actually, I'm going to skip the part where I talk about my model because it's somewhat tedious. And I'm going to jump over to some real spectra, because I want to make sure you know that there's a lot of work going on today on exoplanet atmospheres. And what we want to do is, these are transiting planets. I'll assume that everybody knows what a transiting planet is. And we're talking about transmission spectra, when the light from the star shines through the atmosphere. And we have lots of spectra today. And so I want to show you what these are and tell you a bit about what we've learned. And I know for some of your field, I hate to have to make an excuse, but I know for some fields, you'll see this spectrum and you'll be like, wow, this is terrible. But for the field of exoplanets, we've worked for 15 years, we as a community, to get these spectra like this. So we're very pleased about it. And we see this as a stepping stone to understanding these planets with the first generation, to then later in the future when we have a chance to study smaller rocky planets. So what you're seeing here is HD 189733b. Remember at the beginning of my talk when that was the first star that I went to for exoplanets. It had that planet that was very close to the star. It's heated to about 1500 Kelvin by the star. This is showing you a spectrum, and this is wavelength in angstroms. So here would be 1 micron. Wait. Yeah, this would be 1 micron here. Wait, I got to get oriented here. This is visible wavelengths here. So I guess, yeah, this would be about 1 micron here, and this is extending into the infrared. And what you're seeing is data from the Hubble Space Telescope here, and may I point out this point? And then over here you're seeing data from the Spitzer Space Telescope. Now here in gray, and this is, I'm not going to explain the radius ratio here. For our purposes today, just assume it's a spectrum plotted upside down, but it has to do with how we actually measure the spectrum of a transiting planet. Well, I will say a sentence about it. It's basically that when you look at the planet, it actually looks bigger where there's absorption, because as the starlight shines through the atmosphere, it gets blocked more and more if there's an absorber. And so we actually just plot the size. The planet looks bigger where there's absorption. You can also just think of it as a spectrum. And look at the gray line here, showing you sodium and potassium features, which in hot planets are in atomic form. It's in atomic gas form. Hotter things like our sun, of course, sodium is ionized, mostly ionized, and in colder objects it's locked away in molecules. But it's just kind of lucky, actually, that these planets are the right temperature, these hot Jupiters, to have sodium and potassium because they're such strong absorbers. And this is showing you water vapor features. Now, if you look at the lines, does it match this model? Look at the data as in black, and I want you to look at the spectrum that we were hoping to see. And you see it doesn't match at all, right? What the model is, it's a cloud-free model. If this planet had no clouds at all, we actually expect it to show this. And some people think, oh, we're so wrong, it's so hard. It's not that hard. It's a ball of a gas heated to a certain temperature. And even without a model, we can write down, what are the main molecules. Like we know what the dominant form of oxygen is. It's water, unless the planet had a crazy metallicity. So it's actually not so hard to come up with basically what should be there. If you want to be able to do retrieval and exact abundances, then you need to have a detailed model. But on the whole, we know what to expect. And so why we're so shocked to see this is it means that this hot planet has clouds and hazes. Clouds and hazes are blocking out the atmosphere, actually. And this is kind of a problem for us because we were really hoping to be able to measure a lot of details. And the way I try to describe it is it's like when you fly in an airplane. If you fly up through the clouds and then you look down, you can't see the atmosphere. All you see are the clouds, right? But it's that dense part of the atmosphere where the lines are forming. And so you just basically can't see the features. We think this is actually part of the sodium feature here. It's got really tight error bars, and you'd be seeing just the tip of this line. That's kind of the thinking. But why we're so surprised about this is because this planet is hot. Remember I told you it's 1500 Kelvin. And most particles we know, it's certainly not having water clouds. It's way too hot for water to become a solid. But we actually don't even really know what the cloud particles could be. We're thinking that there's silicates. The melting point of rock is about 1500 Kelvin, so we could have just literally clouds made of rocky particles. I heard pyroxene the other day. It could be some kind of aluminum oxide. So the fact that this has clouds was quite surprising. But at least we can say something definite. And it has this Rayleigh scattering slope, but our own Earth's Rayleigh scattering actually is more like this, straight up, lambda to the -4. So here, it's some kind of, we can get a handle on the particle size, but not really the composition. So now we have another planet. This is GJ1214b, and this data is taken with the Hubble Space Telescope Wide Field Camera 3. And I want you to know that exoplanet science, we're kind of hogging more and more telescope time, because to get this required about 15 transits. So that's a lot of time. The transits are lasting a few hours, and you need data in transit and out of transit. So imagine a moment, 6 hours per transit. This one's a little less, but 6 hours per transit, 15 transits. This is a lot of time, 100 hours. Lots of time to get this. And what this plot is showing you is here, it's showing you the wavelengths in microns now. So this is 1 micron here. This is visible wavelengths. This is near infrared. And what you can see is models in the solid lines. Wouldn't it be great if we could see this? If we could see these huge features, we could do great science with it. But instead, look what happened. A zoom in of this plot in this region here where Hubble wide field camera is working at about 1 to 2 microns. Look, it's another straight line. So this planet, too, has clouds. We think it's just dominated by clouds. This particular planet is let's see, I want to say it's about a 3 Earth radii planet. It's what we call a mini Neptune planet. It's close to an M star. And so we started to see a lot of this. A lot of time went into this. Here's another one, GJ436b. Same kind of thing. We would hope to see a spectrum. This is transit depth now, and this is wavelength in microns. Now it's only 1 to 1.8 microns, but we would expect to see these larger features here from water or methane. And look, just a straight line also. So something's going on in these planets that we're not sure about, and if there's another takeaway you can have is that, yay, we have spectra now, but we're kind of surprised that whatever we're looking at appears to have clouds on it. We don't have any other explanation. Of course, just like in any field, if you have unusual data, everyone wants to come up with a theory. And sitting in my inbox is a paper from one of my former students where we're working on imagining a helium planet. What if our hydrogen escaped, but not helium? And then helium's essentially featureless. We can't see atomic lines with the kind of data that we're getting. And so then you would have a planet that had almost no features. So everyone can make up, you can invent your own theory, which could later be refuted. But for now, let's just say we're puzzled. Okay, I think I just have a couple more spectra. This is showing you another planet, HG 209458, with the Hubble Space Telescope Wide Field 3 camera. And this is showing you wavelength in microns, 0.2 to 1.6 microns. This data is from the Wide Field Camera 3. And now look, you see a feature. And this feature, again, the blue and red are models, and the points are the data with the error bars. And this one we consider a robust detection of water vapor. The giant planets like Jupiter that are warm enough should have water vapor naturally occurring because water is the dominant form of oxygen. So in this case, we do see one. So we have actually lots of planets. And I just actually have one more spectra to show you. And this one is WASP-43b from GTC. And this is by Enrique et al., 2014. And it's showing you wavelength in nanometers because it's working at the visible wavelengths. And what they're trying to do here is detect sodium and potassium. There's a tentative detection of sodium. But I'm only showing this because I want you to know that GTC is one of the most promising ground-based telescopes that will work at visible wavelengths and could conceivably measure the visible wavelengths of many of the planets, many of the hot Jupiters and slightly cooler planets, and also try to look for secondary eclipses. So we have a lot of hopes for GTC, and I was very pleased to get a tour of it. Now, to summarize, this will be new to some of you. So we have this tabulation here. This is not like a robust thing, but it's a, Andras Sam, who's a postdoc in my group, he kind of canvassed the literature and looked at all of them. And here's what you could say about the number of exoplanets where we have spectra that are good enough for us to tell you whether we think they have clouds or not. It's quite a lot, actually. Most of them have clouds suspected. This is showing you cloudy, cloud-free, and cloud suspected. And so, again, we're puzzled because they're hot planets, and we didn't expect that solid particles could form of really any kind and be so massive. So that's where we are in the field of exoplanet spectra. It's only a subset of planets we can study, hot ones, usually big ones, and we're finding that most of them appear to be cloudy. So when I said we know how to identify a planet like Earth, we think so, but we also thought we would understand hot Jupiters. And so lessons learned are that exoplanets are diverse, including their atmospheres, and that clouds may be a limiting factor to observations. So now I get on to my favorite part of the talk. And as Enrique mentioned, it's in the future, because exoplanets, most of it, although it's such a huge field right now, the future is still immense. And that's because, like all of astronomy, every time you have a new telescope on the ground or in space, it opens up things you never imagined. But in astronomy, we are developing the required space telescopes, and we have what we call a two-pronged strategy. One of them is current, so that we will say it's the ground-based and space-based assets under construction. And we will find rocky planets transiting small stars. I know that you have some of the work going on here with radial velocity, Carmen's, and other things. You'll find some rocky planets in the habitable zones. We have an MIT-led NASA mission called TESS, Transiting Exoplanet Survey Satellite, and there's a few people here who are involved. And we'll be requiring some of the telescopes here to do follow-up for radial velocities to help us weed through which are which. But I'm not going to talk about that. I'm going to talk about something in the future. It's the true Earth twins. And the thing about transits is it's the main thing today, right? Because it's the only technique we have to find very small planets right now. And essentially, it's because we're using all visible wavelengths. We get a lot of light, and we've really perfected the technique. But transits are a problem because they're limited to planetary systems with a fortuitous alignment. Planets, stars collapse in a random way, and the stellar inclination axis could be anywhere. And so the planet orbits could also be anywhere. So we want to consider direct imaging, that is imaging Earth on its own. The problem is that Earth is 10 billion times fainter than the Sun. Now, one thing you may not know is that Earth itself, at about 10 parsecs, it's about as faint as the faintest galaxies observed by the Hubble Space Telescope. So think of the ultra-deep field or whatever the latest one is. That's kind of how faint an Earth is. So we know how to observe it, right? Because Hubble, it's in low Earth orbit. It's not a great environment. It's a 2.4-meter mirror. Technically, we know how to do it. The problem that we're working on is how to get rid of the starlight. And one concept we have is we want to block out the light. Imagine putting a giant screen in space to block the light out, and there conveniently are 3 planets. But I want to share with you the diffracted light problem, because actually exoplanets has motivated like a whole branch of optics now. And the way I like to describe this is, okay, this is good because since you're observational astronomers, a lot of you here, you'll understand about diffraction, right? If you have a circular mirror, or in this case we're imagining the circular screen, and you're looking at the star, and you're blocking out the star, or you're looking at the star, you're not going to get a blank image, right? If you block the starlight out, you're going to get the airy ring pattern from diffracted light around the edges. And this is a problem because the first airy ring is actually 100,000 times brighter than the planet you're looking for. So circular screen in space or even a perfect telescope won't do the job. And what people did over like a decade or two is they designed different shapes. So you could imagine that your screen now, or even your telescope mirror, if you could do this, is a very special shape like this star. And in that case, your actual image would look like this. It's very dark on the inside, dark to, well, if you make the shape properly, you could make it dark to 1 part in 10 billion. And all the diffracted light is thrown to the outer edges of the image. And people worked this out in immense detail. There's a group of people kind of mostly in, well, all around the world, but mostly in the USA and France, who actually worked this detail out. So look at that shape. It's a star shape. Now, you can actually put this shape. You could, of course, make your primary mirror like this, but that would be too hard and messy. But what people do is they put a chronograph inside the telescope. It's a special shape. There's many different ways. They can put it the image plane or the pupil plane or other things. And then we also have the concept where we put this outside the telescope. We put a giant screen in space, and we'll block out the starlight, and the telescope will be in this dark hole here, only getting light from the planet. And so I wanted you to hear something you may not otherwise know about, that in the United States, we are ramping up for direct imaging. We believe it's the next thing. After all the transits are just, all done, we've figured out everything we can about the nearest stars. And right now there are 2 studies going on. They were initially called Reduced Scale Terrestrial Planet Finder, but no one likes to call themselves reduced in any way. So we're renamed Probe Class, and there's 2 studies going on. One is on the right, it's the internal chronograph. On the left, it's showing you the star shade. I am pleased to tell you I am chairing the star shade exercise. We have 10 engineers at JPL who are employed to work on the project. And then we have 10 people from academia and NASA centers who are the science team trying to figure out what to do. We've been working really hard for, it's an 18-month concept study. So I'm going to tell you a bit about this Starshade mission. I want to make sure I leave some time for questions, so I've chosen a few to tell you about it. To start with, I'll explain just an animation showing you that a starshade and small telescope could be launched together. And they'll separate in space, and the petals will unfurl from a stowed position. The central truss will expand for the second stage of deployment with the petals snapping into place. The starshade, kind of unfortunately, for the diffraction pattern to work, it not only has to be a very special shape, but it has to fly tens of thousands of kilometers away from the telescope. So there's really nothing easy about this problem. And there it is. It would block out the starlight, and you'd see the planets. In this case, this fake system had an Earth energy bar. So it's hard. It's a very hard problem. But I want you to know that there's no easy way to find an Earth. If you want to do the internal occulter, it's actually just as hard or even harder. But I'm going to explain a couple of key points about it in a moment. I just want to show you now a real video, just so you don't think it's like a concept on paper. There's been, I need to back up here and explain something that for the starshade, you can never do end-to-end testing. Like I got a great tour here of your instrumentation lab, and I saw the Nasmyth mechanical simulator where you can test everything here before going to the telescope. We can't do this for the starshade because it's 30 meters, and it would have to be tens of thousands of kilometers away. So we do 2 things instead. One thing is we test in the environment that's in the lab at 0.1% scale, or actually outside in the desert at 1% scale. We test that the math actually works and try to get down to the 1 part in 10 billion contrast. The second thing we do, and I say we because it's not me, but it's the whole community, is we show that we can fabricate the petal to the required tolerances. To get that perfect diffraction pattern from 1 part in 10 billion, those petals have to be shaped so their width is measured in like 100 microns. And they have to deploy to millimeters. So real tests happen at the full scale to manufacture, to fabricate, and deploy. So that's what this was. This was a demonstration of 4 petals. That's all they could afford. This was from about a year ago, showing you the petals are stowed. They're a special carbon fiber. This is kind of flight-like material, and they're passively unfurling. What you can't see is this longeron here. It snaps out, rigidizing the petals. They made 4 so they had enough interfaces to test. Now this central truss here, we're going to see it expand in a moment, but you know what? That's actually left over, that very truss, from building large radio deployables in space. Now you see the second stage of deployment. I always get asked why there's people in here, but the point wasn't that it deploys automatically, more that each of 25 times or more that it deploys, those petals land in the same place with respect to each other. So that central truss, actually, it's left over from large radio deployables. The giant radio devices listening in from space, they actually, communications, they're made the same way. They deploy in the same way, except for those petals. And so actually this summer, there were 12 undergraduates at NASA. And see how this one is smaller? It's much smaller because these petals were stowed around a truss that it already existed, but they actually, they're constantly making it better. This is all they really need is a smaller one that stows better. Here's a picture of one of the petals that was fabricated to show that these are 7 meters long, very big, to show that they can be manufactured to the right precision. Okay, so regarding testing, I'm probably not going to have time to explain it all. So what I'd like to do, I just want to tell you about one of the testing that's going on. The one in the lab, of course, is the best one because you want to put it in the lab and show that you can reach the contrast required with a star shade. But I think the desert one is easier to understand. This is a figure here showing you contrast parts in 1 part in 10 to the 7. So they actually reached only a few parts in 10 to the 8. They didn't reach near 10 to the 10, but it was their first try demonstrating it in an outdoor environment. On their first try, they reached 1 part in 10 to the 8th. So that's pretty significant. So what it's showing you here is they have the star shade is blocking out the light from an LED fake star and fake planet, actually. And they're just showing you they can recover this planet far away and this planet nearby. And there's some defects in the star shade that make this. But I just got these pictures recently from the desert testing they did in September, about a month ago. And what they did was they went to the Northrop Grumman Corporation. They go to the desert in Nevada. I don't know, have any of you been to Death Valley? It's very dry. The dust actually is a problem. They actually had rain. They had just very bad weather, like all observers, right? You have weather. We didn't think that they have to deal with weather in the desert. And this is the star shade here, okay? And this star shade, actually, it's about this big. It's 1 meter. And those tips are very pointy. If I showed you the tip and it catched on even your jeans, which are very tightly woven, it actually will pull a hole in them. So the shape of those petals is very important. And what you can see here, can you see it? Here's their detector, and this is their light source, and this is spaced out by about 3 or 4 kilometers. Because remember, the distances are very big, and they have the star shade here at the appropriate place. And here it's showing you at night, where they have the LED bank is very bright. And here's, well, they've actually exposed for long enough to make it look very bright. Here's this. You can't see the star shade in the middle. So I just showed this to you to test, but the reason I'm showing you this is because one thing that we're hoping is that we need you to understand that the star shade can be a part of the astronomer's toolkit. And so ultimately what we really need because we have this sort of engineering demonstrations, and then we have to convince people that it's something that actually works. And so what we're really hoping will happen is that someone who's not on the team, but an outside astronomer, will actually make an observation with a star shade. And those people have to have mountains. I'm looking at Rick. I'm not expecting you to do this. Someone in Arizona, but I didn't know that you had so many peaks here. For some reason, I just thought it was Haida. I didn't know there's so many hills. But if you could do this right, you have the star shade, and then you have your detector. And you have to wait for an object to kind of go by. But if you could image a disk or make some kind of discovery, maybe it's not like the biggest discovery ever, but you just image something and do it for real, and someone outside of the actual star shade community, just shows that it works. I feel like the rest of the world would believe it more, believe that it's a real concept. So I spent a lot of time talking about the star shade because it's the thing we work on. But in the future, when we do see this pale blue dot, we have a lot of work to do. You know, we have to understand the background galaxies that might be there. We have to understand how to deal with Zodi if it's there. We have to understand what are the range of planets that we might see. And we have to understand how robustly, if at all, with the first generation direct imaging telescopes, we could really truly identify an Earth. So I said we're developing the required space technology. This decade, we have TESS it's going to discover M-stars, and we'll follow up their atmosphere with the James Webb Space Telescope. But because the number of transits are limited, we really want to be able to search our nearest sun-like stars for direct imaging, and that's what I talked about with the star shade. So to summarize my talk, I wanted you to walk away with the thinking that we feel like as a community in astronomy and planet and exoplanet science, that all the work we're doing, we've discovered so many planets that are interesting in of their own right, but the sort of path is marching down, and we're slowly checking off all the boxes we need. And although it will be a long search, I'm confident that sometime I could come back here, in maybe 10 or 20 years, and in fact, instead of telling you about the future, I can show you the star shade and the results. Thank you for your attention. And while we're doing questions, I'll just leave you with the review article that summarizes everything I said, and it has references, too, on the exoplanet spectra and just the kind of thinking of the whole path forward.
Okay, thank you very much, Sara, for this very interesting talk. So now it's time for questions.
Sara, in your new definition of habitable zone, I have noticed that Mars is included. Can you comment on that?
Yes. Okay, so we really need to get rid of the term habitable zone, and we need to have it defined per planet, because it really depends on the type of planet. Almost where the planet is only one factor, and the other factor is really the greenhouse effect of the individual planet. So Mars, as you know, it has essentially a very thin atmosphere. It's not a strong enough greenhouse to warm it. And so I think we're lost here. We sort of have to make a new definition of habitability per planet.
On the star shape proposal, which it looks very interesting, does this work only in a very narrow wavelength band, or do you can?
The question is about the star shade and what the wavelength band is, because I forgot to mention that, as you know, all optical phenomena, diffraction, refraction, it's very wavelength dependent. And so typically these techniques, they can only work at like a 10% bandwidth. So at 500 nanometers for the internal coronagraph, that's only 50 nanometers. For the star shade, though, it's a little more forgiving, and you can do hundreds of nanometers. So we think we can cover 0.4 to 1 micron in 2 or 3 different groups. And you'd actually have to move the star shade out to compensate.
In the observation strategy, you would move this tens of thousands of kilometers away, the star shape in front of a star, and then you'd have to keep like a permanent truss to keep it in position for a given number of hours or days.
Yes. So the operations of the star shade, it has to move around the sky. The telescope actually, or the star shade, have to realign. It takes about a week to move it in our baseline design mission here. So each year you get about 30 realignments. And you have to plan very carefully because the sun is a problem. And so your actual strategy, you wouldn't believe how many hours we spend thinking about the strategy and our target stars and how we're going to handle it. You have to, once you're in position, you probably don't have to thrust during your observation. And then, you can kind of realign a little bit. So you don't really have to. And your positioning has to be very precise with respect to the telescope. But just like any observation, except for transit precise photometry, it doesn't really matter where you are in the detector. So as long as you're lined up it'll last for however long it takes to integrate. And you can then rethrust and then reintegrate. But I forgot to mention one thing, actually, which I'll see if I have time. I'll add it later if it comes up. But what I want to say is that the star shade does all the hard work. So imagine now for a moment you're on the ground and you have a telescope and you're doing adaptive optics. To do adaptive optics, you either need your laser guide star or you need a bright target star. So the internal coronagraph, it doesn't really work as well as the star shade for small telescopes because you need a bright enough star. And the target stars it can access with a small telescope aren't bright enough for the wavefront correction. And the star shade does all the hard work, assuming you can build it. You're measuring things, like I said, in hundreds of microns and millimeters. And so the star shade actually, for a small telescope, you can do inner working angle and contrast that are way better than anything we've ever imagined. But for a much larger telescope, the star shade isn't such a great idea because it takes a long time to move it around. And if you have a very large aperture, the star shade may be wasted in a way because you can't, the faint stars that you could access with a large telescope, you don't have time to get to them.
Have star shades been thought about? I haven't thought about now at all that it could be done for ground-based telescopes, that you put up in space a star shape that works together with
Yes,
the ground-based
the question is, could we just put a star shade up there and then use ours? Let's see, people have talked about this. It's a bit of a problem because I think the main reason is twofold. One is the distances don't work. It has to be the right distance. So you couldn't do an Earth, but maybe you could demonstrate it. And then where would you be, like geostationary? It's just not the right distance. And you may only have, you know, I think technically it's possible, but I don't think for the cost and expense it buys you enough science.
Sorry, I didn't catch the. So this project will work in the infrared?
The star shade would work at visible wavelengths.
Visible. Why that? Because
Why?
the contrast is much better in the infrared for the
Okay,
planet.
so here you go. So this is really interesting. The contrast is much better than the infrared because the star drops, remember this, and the planet is absorbed radiation. It's re-emitting at its black body. So if you draw a black body of the sun and a black body of Earth, actually in the near infrared it's better. Now there's two reasons. And I want to explain this carefully because the exoplanet direct imaging community realized about quite a while ago that, wait, let me think for a second. Okay, well, there's several reasons. But before we were thinking of doing Darwin, which had several, it was interferometry. Now in interferometry, you're imaging the entire planetary system and then trying to pick out your planet signal. In that case, the Zodi is overwhelming because you're getting Zodi from the whole thing. Whereas at visible wavelengths, you're just getting, you know, little thing, and you get a small amount of Zodi and your planet. So people realize that for the interferometer, you lose out. Even though the contrast is more favorable, the Zodi that's filling your whole image is a big noise source, and it doesn't help. It's easier to do the monolithic telescope and the high contrast. Now, while we'd like to do infrared, the main problem actually is the lambda over D problem. My star shade there, it has 30 meters in diameter. It also follows the lambda over D problem. So instead of 0.5 microns, if we want to go to even 1 micron or 2 microns would be 4 times the size of the star shade. And if we want to go to, you know, 10 microns, all of a sudden now we're having like a 300-meter star shade. And we're very beat upon by NASA and others that we have to have heritage. So our first star shade, we can only have that inner truss as big as the ones that have already launched. So our inner truss can only be 15 to 20 meters, our star shade. So actually it's the lambda over D problem why we can't do the infrared. Now, ideally, we'd want to do the near infrared. Although the contrast is terrible there, it's where all the molecular features of interest are.
I have another question. Can you comment about these very old stars that they have discovered recently, something like 10 billion years old stars, having planets?
Can I comment about the 10 billion-year-old stars?
About what implication may have finding planets in these very, very old stars.
Okay, the question is, what's the implication for finding planets in really old stars? I mean, your answer would be as good as mine. I think it's, I can only say it's good. I think it just extends the comment that all stars seem to have planets, and the diversity is just tremendous.
Okay.
Yeah.
I had a question before, but now another one has occurred to me. How do you move this shield around?
You move it around. So it's a good question, and we need to fix our animation because it'll make more sense. But it has thrusters on it. It just has gas tanks and thrusters, and the star shade actually just moves around. It has got a big spacecraft attached to it. In fact, that truss, inside the truss, that's actually where the spacecraft bus would be. And it would have fuel tanks and propellant, and it would have solar panels spread around it. Now, in one of our designs, the telescope moves. So the star shade goes out there, and it's just kind of doing some fine maneuvering, and we put extra stuff onto the telescope. And the telescope will move around through space. It's a little bit easier to maneuver. But one thing I want you to know is that, just in case any of you are ever involved with like a space telescope, we would like all space telescopes to be star shade ready. That is, you have a telescope, and it would cost tens of millions, which is kind of a lot, but maybe not compared to the whole telescope. And you would put on a special camera, a guide camera, so you could see the laser and LED light bank from the star shade, and a special communications dish so you could communicate with the star shade. Now, in that case, we didn't think it was fair to ask them to stick on a whole lot of extra fuel. We're thinking about in the W1st AFTA 2.4-meter telescope in the United States that's supposed to go forward for dark energy. So we're thinking of both. So yeah, it's a problem. And you're somewhat fuel limited. But in the small telescope regime, you only have a certain number of bright stars you can look at anyway. And so I know clearly I sound like I'm selling here, but there's a sweet spot in you have enough fuel for 3 years. It's a 3-year mission. You know, you have 30 maneuvers a year, and you actually can work this all out. But a lot of time has been thought about which types of fuel to use and how efficient can this be. So it's certainly one of the bigger problems. But it's not as hard as getting the shape perfectly precise and formation flying. So the fuel to just move it around is, in the scheme of things, not the biggest problem.
The original question's much more boring, which was that there's a by extrapolation comment on one of your very early slides about what extrapolating in what sense. I'm not being critical. I'm just curious.
No, it's good because I wanted to.
What's extrapolated and from where?
I wanted to talk about this in a lot of detail. I didn't have time, but
I must be frustrated.
So it's important. It's a good question, actually. In fact, I'll show you. So he was talking about this. Well, okay. So the Kepler space. You weren't, but this is actually related. The thing is, we wanted to know how common are Earth-sized planets in Earth-like orbits about sun-like stars. We were told that we can't proceed with the direct imaging telescope unless we know how common they are. And that was our whole goal. We want to know exactly what's down here. But you know what? Kepler didn't meet its goal, and if you have time, I could explain why. But it was supposed to actually find planets here, and I'll just explain it briefly, and if you want details, ask me after. But its reaction wheels failed at the end of mission lifetime. It was supposed to last 4 years, and the reaction wheels lasted 4 years. I always think of this as like if you ever buy an appliance, like a washing machine, and if it breaks, like the day after the warranty expires. So Kepler did everything right. It should have done it in 4 years, but it turned out that sun-like stars we think now are more variable than we expected. And the team used to joke before the reaction wheels failed that our sun is not a sun-like star. Because our sun, we only had our sun to look at, and the other stars are more variable, like 2/3 of sun-like stars. So Kepler decided this is okay, it's white noise, white variability, we just need 7 years. The mission ended at 4 years, and so we didn't get this part. And so by extrapolation, I actually am going to show you because it's a really good question. We want to know how common Earths are. And I actually just left this off. So let's look at this plot here for a second. And it's showing you orbital period in days, right? And here it's showing you planet size. And so we want it to be in this box here. But there's nothing in that box. We didn't find planets there. And so in this very careful study, they find everything in these other boxes. They find bigger planets and planets with shorter periods. And they do a very specific completeness per box. It's injecting a fake planet for each star and then going through the data reduction pipeline and then saying, could we have found that planet? There's nothing here, so they have to extrapolate. That's what I mean. So by extrapolating, let's say they just make a curve and then they say, okay, there's this many planets of this size in this period, and they're just having to extrapolate because there's nothing in that box. It's just a big caveat because if you just glance through a popular astronomy magazine or a News and Views article in Nature, you may not realize that when they're claiming that 20% of sun-like stars should have an Earth, actually it's really based on all this other stuff, and they're extrapolating. Does that help?
Yeah, I was going to add with respect to the Mars comment that our planet was completely covered in ice several times for large, long periods, which is actually a really encouraging thing for me when I'm reading about this from a different field, in the sense that the universe can do what it likes.
I'll make 2 comments on that, actually. Yeah. And one of them is that, yes, it's frightening at our own Earth because of the Milankovitch cycles. You know, our own Earth, we have like an eccentricity, and, you know, we very small, right? And we have a tilt, and we have a precession. And when all of those 3 things, they're so tiny, when they conspire the wrong way, our Earth gets glaciated. That's what we think. And it's shocking, right, that just these tiny changes. But I want to say one thing just to update you. This may be more of an offline thing, but it's also relevant for people working on Earth. Now people don't think Earth was, some people do not believe that Earth was entirely glaciated. And the reason is because they got the ice albedo wrong. The albedo, they think ice is really bright, but this won't be meaningful here. The people in Canada figured this out because they have sea ice. Sea ice is very dirty, actually. It's if you ever go up to the Arctic, especially in springtime when that sea ice has been there for a long time, it's very dark. And so now they're finding that in the model sense, because they hadn't found observational evidence that it was fully glaciated, so we don't really know. But it's correct that our Earth was glaciated, and that small changes in our own orbit, we don't even totally understand that. So yes, it could really be planet dependent.
Okay. So,
yes, in your review, I noticed you left something out, which I believe is going to play a major role, which is a really high-resolution spectroscopy from ground-based telescopes, because that really allows us to get rid of our own atmosphere. Can you tell something about this?
The claim is that really high-resolution spectroscopy. Do you mean like in the visible or near-infrared, or? Yes. Are you talking about like the cross-correlation or just other stuff? Yeah. Right. I mean, there is one really amazing technique that uses cross-correlation. And what they rely on is, molecular bands are these huge, big features. Well, that's a rotational vibrational band. And actually, the rotational features, anyone who works on brown dwarfs or other things with molecules, they're very tiny. They're so tiny. So that huge band is actually made up of hundreds of, or thousands, or tens of thousands of these little lines. And actually, people have used very high-resolution spectroscopy. It must be like around the order of 75,000 spectral resolution. And they use a cross-correlation technique. So they have like a spectrum, a theoretical spectrum of the atmosphere, just on one molecule in a very narrow wavelength band. And they know that that planet is orbiting, so it's got a shift that's changing, like a Doppler shift. And they can actually measure the planet and star in the combined light. And they can actually, by altering that, measuring the best fit of that correlation, depending on the theoretical spectrum, they can actually identify, A, that the planet is there, winds on the planet, and even abundances. So there's a huge market for that. It depends, of course, on the planet moving fast enough, and it's probably limited to planets with 10-day period or less. But yes, there's a huge field right there. But it's such a big field now. Even in atmospheres alone, we couldn't cover everything in the time we had here.
Okay, so if there is no more question, just to remember that now we have the scientific coffee in the canteen, so you can speak with Sara a bit more. Well, let's thank again her for her talk. So.